So these are the questions I want to talk about today. Before we get started, there's a couple things I wanted to add to yesterday's lecture. One is a point that I omitted, which I think is worth at least mentioning. There was a gap in some sense. Remember, last time we were talking about calculating intersection products of cycles in the Grassmannian specifically of lines in P3. And we said, for example, that if we wanted to intersect two such cycles, yeah. Pardon? Oh, the light for the blackboard, yes. There we go. And that's both. Okay, good. Thank you. We said if we wanted to calculate the intersection number of two cycles, like, for example, we said we want to calculate sigma 1 dot sigma 2, 1. We say we would choose representative cycles for those classes. So that would be sigma 1 of a line L intersects sigma 2, 1 of, well, that would be a point in a plane. And we would take their intersection and take their cardinality, which we could then evaluate. That's not an issue. If L, P, and H are general, again, this is just the number of lines such that, sorry, I guess I should give them a different name, lambda, such that lambda meets L, and of course P is in L, is in H. And then we drew the picture. We said, here's the plane H, here's the point P, here's the cycle of lines in the plane H through the point P, and here's our other line L, and we see that this intersection consists of one point. There was one issue that we didn't address. The first equality, that this intersection number is equal to the cardinality of the intersection of the cycles, presumes that this intersection is transverse. And we didn't check that. And I repeated this mistake, if you want to call it that, over and over and over. Every time I say, take general Schubert cycles and intersect them, and I just assume the intersection is transverse. So let me just say how we would go about doing that. And there's two ways, basically. Well, there's many ways, but two in particular. One is to invoke a theorem of Kleinman's. So Kleinman says that if X is a homogeneous variety, so if G, a group, acts transitively, I'm going to state this in general form, not specifically for the Grassmannian, on X, and A and B are cycles on X, then a general translate of one will intersect the other generically transversely. Then GA will intersect B generically transversely. Again, I'm in the market for an alternative notation for this, for a general G. So a general translate of one cycle will meet another given cycle transversely. Now, in this case, the Grassmannian is a homogeneous variety. The automorphism group of P3 acts transitively on it. And it carries, when I say take P and H general, that means this Schubert cycle, for example, is a general translate of a given Schubert cycle. So we have transversality. Now, I have to say in honesty that this is, Kleinman's theorem works as stated in characteristic 0. It works in characteristic P subject to a slightly stronger hypothesis. The group action has to be not only transitive on points, but transitive on non-zero tangent vectors. That, for example, applies to projector space. If you have any 2 points and a non-zero tangent vector at each, there's an automorphism of the projector space that carries one tangent vector to the other. It's not true for the Grassmannian. If you look at non-zero tangent vectors, for example, to the Grassmannian G13, there are, and this is something I'm leaving as an exercise for you guys to think about, there are exactly 2 orbits. And so it doesn't quite apply in characteristic P. If you wanted to verify transversality in characteristic P, you would have to go to plan B, which is you simply write down the tangent spaces. to these supercycles, and you verify that for a general choice of P and H, this intersection is transverse. So that's just a remark that I think.
Well, isn't there some way of looking at the picture and saying, sure, it looks transverse?
Well, you know, the thing is, it's fairly subtle. You know, if you look at something like,
you wiggle the line a little bit, and you wiggle the line a little bit, it's still the same thing.
But the point is, no, that's exactly the issue. You'd like to say that, you know, if you vary P and H or vary L equivalently, that the cardinality remains the same. That doesn't mean it's transverse. It could be tangent for every choice of L, P, and H. Now that doesn't, you know, that's not going to happen, right? And it doesn't happen. But technically you need to verify that. And there goes another 50 pages. All right. And there are some subtleties here. I mean, it should be said that if you, but let's not get into this because we have a lot to talk about today. The other thing I wanted to say was, of course, and this is not a surprise, and I won't belabor the point, but the sort of Schubert calculus that we developed for the Grassmannian of lines in P3 yesterday can be carried out for any Grassmannian. Okay, so let me just make that remark that we have a similar description of the Chow ring of the Grassmannian GKN for any K and N. In the sense that we can first of all describe a set of additive generators, which are Schubert cycles. If we take the set of K-planes in Cn, we choose a flag in Cn, a sequence of subspaces of each dimension, nested inside one another. And if we look at the locus of planes that have a specified dimension of intersection with each flag element, that will, as we saw in the case of the Grassmannian lines in P3, that will be an affine space. And those locally closed subsets of the Grassmannian will give an affine stratification, and it follows their closures, the Schubert cycles, the subvarieties defined by requiring that the dimension of intersection with a K-plane with each flag element is greater than or equal to a specified dimension. Those Schubert cycles freely generate the Chow ring. The problem is then, how do we calculate intersection products? And that is actually kind of subtle. Basically, and strangely enough, there's a lot of sort of qualitative questions that are open. There are algorithms for calculating the intersection product of any two Schubert cycles. First of all, we can do like we did yesterday and do the intersections in complementary dimensions very easily. That's very straightforward. And of course, once we know the intersections in complementary dimensions, we can use that trick, or that method of undetermined coefficients that we employed for the Grassmannian of lines in P3. We can do that in general. It reduces the problem of calculating an intersection of any two Schubert cycles to the intersection of three Schubert cycles in complementary dimension, like when we had sigma 1 squared dot sigma 2. Now, in the case of the Grassmannian of lines in P3, it was pretty clear. In general, it may not be. And in fact, no one, you would like to think that you would at least be able to look at three of those Schubert cycles whose codimensions add up to the dimension of the Grassmannian exactly, so they should intersect in a finite set of points. You should be able to say when that intersection is empty or non-empty. And I don't believe there's an answer, a closed form answer to that question. Again, there are algorithms that you can run, and they will produce the answer, a number that's either 0 or 1 or possibly larger than 1. But I don't know of any formula that looks at the Schubert indices, a triple of Schubert indices, and tells you whether it's the intersection is empty or not. So there are a lot of qualitative questions still open about Schubert calculus in general. And again, the whole area is called, in some sense, Schubert calculus. What I would suggest as an exercise is try to work this out for the next simplest case, which is unambiguously the Grassmannian of lines in P4, or equivalently by duality, the Grassmannian of two planes in P4. And in fact, Seriously, if you want to sort of test your understanding of what we did yesterday, and if you want to develop this knowledge, this is a wonderful example to work out. It's also going to be relevant when we ask a question like the third question here. If we look at a hypersurface in P4, right, and we ask whether it has lines, we are going to be working, as we'll see in a moment, in the Grassmannian of lines in P4. Okay, so that's I think all I'm going to add to what I said yesterday. Let's get started on today's topic, and that's sort of these questions here represent a sort of a way of approaching what we're going to do today. As I said, we're going to introduce the notion of Chern classes, and which is a tremendously effective tool for answering a lot of enumerative questions of this sort, and we're going to approach it a priori as a technique for answering these particular questions. I'll tell you what, though, before we start even thinking about Chern classes, let's take a moment out. Today, we're going to talk about lines on hypersurfaces, and we should always start by making, I think, a naive dimension count, just to sort of see what we would expect to happen. You know, we always should go into these problems with an a priori expectation. So I want to say, let's let X be a hypersurface of degree D in Pn. And I ask, do I expect a general such hypersurface to contain a line? There's a standard technique for answering that. I think this is, I first saw this in the very first chapter of Shafarevich's book, and it made a lasting impression on me. The standard technique is to introduce an incidence correspondence. You let Pn, first of all, be the space of all hypersurfaces of degree D in Pn. And as Robin pointed out in the case of D equals n equals 2, this is a projective space. It includes some things that you may not think of as nice hypersurfaces, multiple planes and so on, but well, we're going to include them anyway, for the sake of completeness. Of course, as yesterday, I want G1n to be the variety of lines in Pn, and I want to look at the incidence correspondence, phi, which consists of pairs, a hypersurface X and a line L, such that L is contained in X. And that admits projections to the projector space of all hypersurfaces and to the Grassmannian. And here's the point. The reason why we introduced this, basically, we're asking about, in some sense, the fibers of phi over Pn. For every point here corresponding to a hypersurface X, the fiber of this incidence correspondence is, by definition, just a set of lines lying on that hypersurface. So we want to know about the map from phi to Pn, but we have another way to approach phi, which is via the map to the Grassmannian. And that's particularly well behaved. We know, of course, that this is irreducible. The Grassmannian itself is irreducible of dimension 2n minus 2. What's more, the fibers of this map are very easy to describe.
2n minus 1? Oh, 2n minus 2.
2n minus 2. Or twice n minus 1. No parentheses. See, if I fix a line, right? And I ask, well, suppose I put the shoe on the other foot, so to speak, for a fixed line, what is the set of hypersurfaces that contain that line? Now I'm looking at polynomials in the big projector space Pn, whose restriction to that line vanishes identically. Now if I write down the restriction of a polynomial to a particular line, I just get a polynomial of degree D in one variable, which has D plus 1 coefficients, which are linear functions of the coefficients of the original polynomial. If I set them all equal to 0, I get a linear subspace of this projector space P capital N of codimension D plus 1. So the fibers here are just projector spaces of dimension n minus D minus 1. very, very sort of relatively, I should say, easy to see. And the conclusion from these two facts is that phi, capital Phi itself, is irreducible of dimension capital N plus 2n minus d minus 3. Okay. And now that tells me, at least dimension theoretically, what I would expect to see when I look at the map from phi to Pn. So the conclusion in particular is that if 2n minus d minus 3 is negative, then a general hypersurface x, again, of degree d and p little n, will contain no lines. We've proved that. We've calculated the dimension of phi exactly. And of course, if the dimension of phi is strictly less than capital N, this map cannot be dominant. The other part we haven't proved, but I will assert it anyway. I'm kind of shameless that way. If 2n minus d minus 3 is non-negative, we would expect, okay, I'll say it that way. We expect that a general such x contains a family of lines of dimension of that dimension, 2n minus d minus 3 dimensional family of lines. So, I mean, think about this just in the case of n equals 3, for surfaces in P3. You know this, in some sense, at least the first three cases. If D is 1, right? Well, if you're looking at a plane in P3, that, of course, contains a 2-parameter family of lines. A quadric surface contains a 1-parameter family of lines. A cubic contains a finite number of lines. And, of course, as we proved, a general quartic contains no lines at all. So in that context, the first two questions we're asking here are simply, what's the degree of the map from phi to Pn in case n is 3 and d is 3? The second question is actually something that is not nearly as well known. In the case where we're looking at quartic surfaces, degree 4 surfaces in P3, what we see from this dimension count is that the image of phi will be a hypersurface in Pn. In other words, in the space of all quartic surfaces, in that P34, there'll be a hypersurface. The set of quartics that contain a line will form a hypersurface. What we're asking here is if we take a general pencil of quartics, in other words, we take a general line in that projective space P34, how many times will it meet that hypersurface? In other words, what is the degree of that hypersurface? Another way to say it is, suppose I write out, well, let me just make that remark. This question here amounts to saying, if I write a quartic polynomial, so f of x, well, let me just use my indices here, z0 up to z3. That's going to be a sum of ai z to the I. Again, this is going to be a quartic. So it has 35 coefficients here altogether. And the condition that the zero locus of this polynomial, that surface in P4, the condition that the zero locus of this polynomial contain a line is a polynomial condition on the coefficients. There's a single polynomial on the 35 variables ai that tells you, that vanishes exactly when the corresponding surface contains a line. I'm asking, what's the degree of that polynomial? And I can't resist telling you the answer. It's 320. But now, that actually has some significance. You think about it. This is a polynomial of degree 320 with 35 variables. The number of coefficients in such a polynomial is sort of on the order of magnitude of the number of particles in the universe, at least by current counts. You're not going to write down that polynomial. Not unless you have a very efficient system for encoding it. and the use of pretty much all the particles in the universe. So in some sense, asking for the degree of the polynomial is the sort of question that we might be able to approach, might be able to answer. We're not going to be able to write it down explicitly. Okay. Now let's get started. How do we solve these problems? You see, this is, unfortunately, we come now to a sort of dirty little secret of algebraic geometry, or algebra in general, that we don't know much about polynomials of degree 3 or more. I mean, we'd like to think that we can manipulate them, that we know something about them, but, you know, I'm going to be talking, I guess, on Monday in Cordova about this, but, you know, if I write down a general cubic polynomial in P5, a general cubic fourfold, we don't know whether that's a rational variety or not. We can't solve it in some sense, and we don't even know whether it's possible to solve it, whether it's possible to write down all the solutions parametrically in terms of 4 free variables. So we don't know how to solve a cubic polynomial, is what I'm saying. We do know how to solve linear polynomials. We're pretty good at that. And we know, to some degree, how to handle quadratic polynomials, though when there's more than one quadratic polynomial, it gets a little bit dicey. But basically, you know, linear polynomials are the ones we know how to deal with. And the reason I mentioned the degree, you know, the answer to question 2 here is because I want to stress that this is not a simple polynomial. This is a complicated polynomial. How do we approach something like that? Well, there's a technique of linearization. And let me just say, first of all, what it is, and then we'll see how it applies in this particular circumstance. We convert a polynomial, this is a process that converts a polynomial of higher degree, and again, by higher, I mean 2 or more, into a family of systems of linear equations. So we reduce the degree to 1, which is good, but we pay a price in 2 respects. We're replacing, for example, a single polynomial with a system of linear equations. That's not so bad. We know how to solve systems of linear equations, not just one linear equation. But we also have to talk about a family of them, and that's where the whole idea of vector bundles and Chern classes is going to arise. So I'd like to use this example as a way of introducing these notions. And in fact, the approach is already suggested here. In other words, in this case, instead of asking if I have a surface S in P3, for example, which is given as the 0 locus of a homogeneous polynomial. This notation V of F just means the 0 locus. I guess Diane's been using it, so that's okay. Does that surface in P3 contain some line, or a line? We ask, does in particular, does S contain a particular line? You see, remember when we looked at this incidence correspondence, that was our key observation. That if we fix a line, if we fix a point in the Grassmannian, then the condition that a surface or hypersurface contain that particular line is it's a system of linear equations, a system of B+1 linear equations. The problem here is that we can't just ask this for a particular line, we have to ask this simultaneously for every line. And that's where we get a family of systems of linear equations. This is a family parameterized by the set of lines, the Grassmannian of lines, in this case in P3. So now let's formalize that a little bit. Now, when we talk about a system of linear equations, the way we would think about that, at least in modern terms. It's not so much a, it's basically we have an element of a vector space and we want it to be 0. What's the vector space in question? Well, again, we said that. If we have a line in P3, a point in the Grassmannian, we want to look at the space of polynomials of degree d, homogeneous polynomials of degree d, on that line. And what we want is the particular point in that vector space, namely the restriction of f to that line. We want that to be 0. That's our system of linear equations. So that suggests that we write this, that we introduce a vector bundle over the Grassmannian, whose fiber at each point is that vector space. So we introduce, I'm just going to call it E, a vector bundle. E, this will be of rank 4, on the Grassmannian of lines in P3, and it's going to be characterized, roughly speaking, by saying that the fiber of E at a point L is just the space of homogeneous polynomials of degree D. Well, let's be concrete. Degree 3, we're looking at cubics, on L. It's a very sort of concrete object. If you want to make it a little bit less fancier, you call this, of course, H naught of OL3. But this is what we mean by it. So this gives us a family of vector spaces parameterized by the Grassmannian of lines. For every line, we get a vector space. And these vector spaces fit together to form a vector bundle over the Grassmannian. And finally, we get a global section, which I'll call tau f, of this bundle E by setting its value at a given point L in the Grassmannian equal to nothing more or less than the restriction of f to that line. In other words, if I have a homogeneous cubic polynomial on all of P3, its restriction to each line gives me an element of the corresponding vector space, and that gives me, in other words, a section of this vector bundle. And the set of lines L contained in S, again, S is the 0 locus of f, is exactly the set of zeros of this section tau f. So we've set up the problem. Again, we've converted a polynomial problem into a family of systems of linear equations, which we think of as the equation that that a certain section of a vector bundle vanish. We want to ask, does it have any zeros, and if so, how many? In the case of the cubic surface, we expect that it will have a finite number of zeros, and we want to count that number. And more generally, of course, when you have a positive dimensional family of lines on a general hypersurface of degree d and Pn, when this number is strictly positive, we can ask correspondingly for the class of that locus of lines. You know, if we have something like, think about this yourself, and you can do this. If we have a quadric surface in P3, it has a one-parameter family of lines. That one-parameter family of lines corresponds to a curve in the Grassmannian. And we can ask, what's the class of that curve? So that's sort of a more general setting. All right, so now let's see where we are. Where we are is we're going to make a definition. I guess maybe I should say one more thing. Now let's just do it this way. Let me just say this. Any questions up to this at this point? All right. So definition. Now I'm going to go from, for the purpose of the definition, I'm going to go from specifically the Grassmannian G13 and this particular vector bundle to just a general smooth projective variety and any vector bundle. So X is a smooth projective variety. And E to X is a vector bundle. And I'm going to have to specify its rank. Let's call it R. And if tau is a global section of E transverse to the zero section, or generically transverse, there's always a hypothesis of at least generic transversality in this case, then we define the top Chern class. This is the rth Chern class. To be just the class of the locus where that section is vanished. So the class of the locus of zeros. Now, you should be screaming at this point, that depends on the choice of tau. I want a function only of E. Now, in fact, though, here is, we can use linearity. If tau and tau prime, there are two such sections. You get a family of sections by taking linear combinations of them. In other words, we could take the zero locus of alpha tau plus beta tau prime equals 0, where alpha and beta are just any pair, not both 0. And this gives me a family of such zero loci interpolating between the zero locus of tau and the zero locus of tau prime. So they are, any two such sections will have rationally equivalent zero loci. So it makes sense to talk about the class of the zero locus of a section. Okay? And now, for reasons that are both dictated by use, if you want, no, there's the second question, still there. If you think about how to set up that problem, how many elements of a general pencil of quartic surfaces have lines? We're going to, I'm just going to say this because I want to just go ahead with the definition, but in order to answer that, we're also going to have to look at the locus where two sections of a vector bundle fail to be independent. So, in general, we're going to define CR minus K of E to be the class of the locus where exactly K plus 1 sections of E fail to be independent. So first the top Chern class independent. Yeah. Okay. The definition of the top Chern class is just the case K equals 0. And this goes all the way down from K equals 0 down to R minus 1. So we have Chern classes correspondingly C1, C2, and so on. And the general definition is it's the locus where a collection of sections fails to be independent. Again, sort of the one that, in this context at least, is most commonly invoked is simply the top Chern class. But you'll see now, in a moment, that in fact, in order to effectively calculate these things, we need to introduce all the others as well. So, having said all this, we can now, we have this, we've got introduced this vector bundle. We've described the locus of lines on a cubic surface as the zeros of a section of that vector bundle. And now we can say what that class of that is. It's just the top Chern class of the, I guess I should say one more thing here. This class CR, this, again, if we assume that this section of E, if E has rank R, and this section is generically transverse to the zero section, the zero locus will occur in codimension R. It's very concretely. Locally, if we trivialize the vector bundle, we can write a section as an R tuple of functions. And to say it's transverse is to say that they form have independent differentials, those sections. Those functions have independent differentials at a general zero, which is to say in particular that it's codimension R. So this is a class in A upper R of X, and this, likewise, is in A upper R minus K of X. So the Chern classes form a sequence of classes associated to a vector bundle ranging from codimension 1 up to the codimension equal to the rank of the bundle. And now we can reinterpret this as saying that the number of lines on a general cubic surface, so the expected number, is just the top Chern class C4 of this vector bundle E that we introduced over there. This is an element of A4 of the Grassmannian of lines in P3. And of course that is the zero-dimensional Chow ring, or Chow group, and that's isomorphic to Z. So that's our answer. Well, you should be demanding your money back. What have I done so far? Let's stop for a moment, let's pause, and let's see what we've got. Basically, we've got nothing. All we have done is to package our ignorance. We have sort of said, we don't know what this number is, but we can give it a fancy name. We can call it a Chern class. We've just moved our ignorance from one place to another, essentially. So far, we have accomplished nothing but just to introduce some new definitions.
So could you solve the same problem the way you did yesterday? It was some intersection of Schubert cycles and Z1.
No, I see, that's a good point, and I wish I'd thought to make it. Yeah, the problem here is if we look at a cubic surface, we want to know the condition that a line be contained in that cubic surface can't be broken up into a combination of separate conditions. You can't say a line lies on the cubic surface if it satisfies the following conditions, each of which would correspond to a Schubert cycle or a class in the Grassmannian, a cycle in the Grassmannian whose class we could calculate. So yeah, this would be one way to think about the problem. In fact, we should have done this right off the bat. We should have said, could we apply the standard Schubert calculus this way? Can we express the condition for a line? Can we express the condition that it lie on the cubic surface as a combination of conditions, the class of whose cycles we can calculate? And the answer, unfortunately, is no. It's just either it is or it isn't on the cubic surface. Actually, that's, no, I think I better leave it at that. So that's our situation. Okay, so, but now, yeah.
What happened if the bundle doesn't have sections?
Well, this doesn't work so well as a definition then. The answer is we can always tensor it with a line bundle until it does have sections. That gives us a definition of the Chern classes of the tensor product, and from that we can write down as polynomials in those Chern classes, we can write down the Chern classes of the original bundle. It's awkward, but in some sense what you might want to do is think of this not so much as a definition of the Chern classes, but as a characterization of Chern classes. That's presuming you have another definition that somewhere else that you can use. The problem is I don't know of a really good one. At the end, in some sense, the best way to think of Chern classes is, the best way to define it is axiomatic. They have certain properties. And this was Grothendieck's, I guess, idea. And you characterize Chern classes by, as a sort of transformation of functors having this list of properties. But at the end of the day, you then have to prove that there exists such an assignment, and you're back where you started in some sense. But it's not a bad way to think about it. And this, as I said, if you have an alternative definition, you could think of, you have the luxury of thinking of this as a characterization of Chern classes.
So another question. In
Yeah.
this particular case, maybe you're going to do this next. In this bundle E, you define somehow, some other.
Yeah.
Can you express it in terms of the O1 on the G13 and stand?
That's exactly what we're going to do. That's exactly what we're going to do. So the point is, let me just say this now, this is exactly what the next sentence that was going to come out of my mouth. We have so far achieved nothing, right? What makes this actually work, and not just work, but be one of the most powerful computational tools in algebraic geometry, is that Chern classes, as we've defined them, and for no visible reasons based on the definition I've given you, they satisfy a whole series of relations that allow us to calculate the Chern classes of a given vector bundle in terms of Chern classes of simpler bundles. That's what makes it possible. That's what makes this more than just, again, a repackaging of our ignorance. It allows us to say, well, I can express E in terms of simpler bundles and use that expression to calculate its Chern classes. So that's the next thing. That's what I want to do for the remainder of this hour, assuming I have a remainder of this hour. I'll have a little bit of a remainder of this hour. I want to tell you the basic properties of Chern classes, the ones that will allow us to carry out this process. Then I want to tell you how we can express E, as Robin suggests, in terms of simpler bundles whose Chern classes we can calculate directly. And we'll put it all together, hopefully in 17 minutes, and we'll come up with the answer. So, properties of Chern classes. And this is what really makes it the one thing I want to introduce before is just notation. For reasons that you'll see in a moment are just useful for convenience or efficiency of notation. What's very often you do is you take the sum of all the Chern classes, where you formally define the 0th Chern class to be just the fundamental class of the base variety. And you write that, you call that the total Chern class, which you write without subscript. So this is 1 plus C1 of E plus CR of E. And of course, this is no longer homogeneous. It just sits in the total Chow group of X. So 1 here refers to the fundamental class, the unique codimension 0 generator. And the rest are just the Chern classes. So the first thing to say, and this is the famous Whitney formula, it says that if I have a 3-term exact sequence, 0 into E, into F, into G, of vector bundles, if this is exact, and again, I mean E, F, and G are vector bundles, then the Chern class, the total Chern class of F, is the product of the Chern class of E and G. This is either called the Whitney sum formula because it corresponds to, in some sense, a direct sum of vector bundles, or it's called the Whitney product formula because it expresses the Chern class as a product. I'm just going to call it the Whitney formula to avoid that whole linguistic issue. This was a very basic formula. It's a very interesting exercise to think about, at least, proving this formula based on this definition. This is, by the way, this definition is very close to the original definition. Chern classes were not defined by Chern. They were defined by Stiefel and Whitney, maybe 10 or so years before Chern proved his theorem calculating Chern classes in terms of curvature matrices. And they define them as obstruction classes, which is a very close relative of this definition. It avoids the issue you asked about, what if you don't have any sections? But it only works in ordinary homology or cohomology. And with anyway, Whitney proved this, and but it's kind of a slog. The second thing is very simple. If A and B are line bundles, I want to tell you what the tensor product is, what the Chern class of the tensor product. And there is only, if it's a line bundle, of course, there is only one non-trivial Chern class, which is the first Chern class, and I want to say that the Chern class of the tensor product is the sum of the Chern classes. Now that one you can see. If A has a section, right, which vanishes along a certain divisor, and B has a section that vanishes on another divisor, then the tensor product of those sections gives a section of A tensor B that vanishes along the union of those divisors. So this one at least is not a problem. Well, third one goes back to being a problem. This is going to be hard even to state. Any formula for relating the Chern classes of vector bundles that holds under the additional hypothesis let's write this in one line. Hypothesis that the bundles split. In other words, that they are direct sums of line bundles, holds in general. This is called the splitting principle. And again, it's a key computational tool. It may sound like it's not clearly defined, but I'd like to sort of illustrate it by the example of the problem that we're working on right now. So, those are properties of the Chern classes. And now what we're going to do is we're going to go ahead and use these to calculate C4 of E. This is a good example of how we do this. So the first thing in order to apply these ideas, we have to relate the bundle E to simpler bundles. And Robin suggested already, I don't know if you guys could hear, but he suggested the way to do that. He says, look, this is the vector space of cubic polynomials, homogeneous cubic polynomials on the line L. That's the fiber of E at each point. Okay? One way to describe in multilinear algebraic terms the space of homogeneous cubic polynomials on a line is as the symmetric cube of the vector space of linear forms. So in other words, this, again, if I can use the cohomological, this is just sim3 of the vector space H naught of OL of 1. This is a, do I have enough parentheses? No, one more. This is a two-dimensional vector space, the space of homogeneous linear forms on L. And if I take the symmetric cube of that vector space, I just get the space of cubic polynomials. So that suggests that we introduce a sort of auxiliary bundle, actually a very fundamental one, whose fiber at every point L is this vector space, this simpler vector space. So we let S star, I'm not going to explain this particular notation, be the vector bundle on the Grassmannian G13, whose fiber at a point L is just the space of homogeneous linear forms on L, or again, in fancier language, H naught of OL of 1. Well, this is supposed to be a simpler bundle. It looks simpler. It's linear rather than cubic, which is nice. Can we calculate its Chern classes? The answer is yes. I suppose I want a section of this bundle. Suppose I want to specify a linear form on every line in P3 simultaneously. How do I do that? Well, I mean, I got a section of this bundle E by taking a single homogeneous cubic polynomial in P3 and restricting it in turn to every line. You can do the same thing here. So if L is a linear form on P3, so just a homogeneous linear form on P3, linear combination of the homogeneous coordinates, then we get a section, tau L, of this bundle S star in the obvious way by saying tau L at a point L is just the linear, I'm sorry for the too many L's, the linear form L restricted to L. Now, if I look at now I want to know, where does this section vanish? Well, when is the linear form on P3, when is its restriction to a line identically 0? When the line lies inside the 0 locus of L on P3, which is a plane. So that, in particular, the 0 locus of tau L is just a Schubert cycle. It's the cycle of lines lying in a particular plane. So that tells us C2 of S star is just the locus of lines L contained in the 0 locus of little l, which is the Schubert class sigma 1. That worked. So let's do C1 now. Well, to do C1 by our definition, now erased, we need to have two sections. So let's let L and L prime be linear forms. And the question is, where are the corresponding sections, tau L and tau L prime, where are they dependent? Well, what does it mean to say? This is, again, the restriction of L and L prime to a line. If I have two linear forms on a line, what does it mean to say they're independent? Many ways to say. They're multiples of one another, or they have the same 0 locus. Well, think about it. L intersects, L vanishes on some plane, right? L prime, I'll call that plane H. L prime vanishes on another plane, H prime. And for a general line L in P3, the 0 locus of the restriction, of the two restrictions, will just be the 0 loci, the intersection of that line with the two planes. When are they the same? When the line meets the common 0 locus. So the point is, the locus, these are dependent if and only if L, I guess I want to say tau L and tau L prime of L are dependent if and only if L intersects the line, which is the common 0 locus of L and L prime. And so in particular, what we see is that C1 of S star, again, that's a Schubert cycle, is sigma 1. So we got the Chern classes of the simpler bundle S star. And think again about what we're saying. The point is, we don't know a priori know about cubics, but we sure do know about linear forms. And that's reflected in the fact that we are able to calculate the Chern classes of this bundle, S star. Now we want to build up E out of this bundle S star by taking the symmetric cube. So now I want to just assert one fairly standard linear algebraic fact. I just want to say, if I have two one-dimensional subspaces, or two one-dimensional vector spaces, so A and B are one-dimensional vector spaces, then the symmetric product, well, let's say specifically Sim3, of the direct sum is itself a direct sum. It's A cubed plus A tensor B squared plus A squared, I should put the square here to be consistent. A tensor B squared, direct sum B cubed. Okay. Now, that doesn't seem to apply. And the same thing applies to vector bundles. If you have two line bundles, and you take the symmetric cube of their direct sum, we would have a decomposition of that as a direct sum of four line bundles. That doesn't seem to apply. Because the bundle S star, in fact, is not a direct sum of line bundles. Okay? But the splitting principle says that that's okay. Let's just assume it is. Counterfactual. It's not. But if we assume it is, okay? If S star, as a vector bundle now of rank 2, were the direct sum of 2, what could we say about the Chern classes of those? Let's say let's give them names. Say the first Chern class of A is alpha, the first Chern class of B is beta. Well, by Whitney's sum formula, it would follow that C1 of S star is, on the one hand, sigma 1, we just calculated that. On the other hand, by Whitney's sum, or Whitney formula, it's the sum of the first Chern classes of these two. And likewise, alpha times beta is the second Chern class of S star, which is sigma 1, 1. Now, if this were the case, then our vector bundle E, the one we really want, right, would be a direct sum of A cubed plus A squared B plus AB squared plus B cubed. And so in particular, the Chern class, the total Chern class of E, would be the product of the total Chern classes of these line bundles. And by the second basic rule for Chern classes, we know what those are in terms of alpha and beta. This would be 1 plus 3 alpha. This would be 1 plus 2 alpha plus beta. 1 plus alpha plus 2 beta. And the last one is 1 plus 3 beta. All right. We come now to the finish line. Okay, so we can express in particular the fourth Chern class. Fourth Chern class of E, well, we just take the terms of degree, homogeneous degree 4 in this product, and I'll collect them this way. That's 3 alpha times 3 beta times 2 alpha plus beta times alpha plus 2 beta. That doesn't seem to be much use because, for one thing, alpha and beta don't exist. They're just fictional classes, right? Because again, S star does not in fact split. But, again, if they existed, we would know at least some of their sums and products. Specifically, the elementary symmetric polynomials in alpha and beta would be expressible in terms of actual classes on the Grassmannian. And since this is visibly a symmetric polynomial, that means we can express it in terms of the elementary symmetric polynomials and convert this to an expression involving Schubert classes. Specifically, this is 9 alpha beta times, 2 alpha squared plus 5 alpha beta plus 2 beta squared. This, by what we just said, is just 9 times sigma 1, 1. This expression here, I can write that again as a polynomial of the elementary symmetric polynomials, and specifically is twice alpha plus beta quantity squared plus 1 more alpha beta. So this becomes twice sigma 1 squared plus sigma 1, 1. We know how to multiply this out. We did that yesterday. That's 9 sigma 1, 1 times 3 sigma, sorry, let me write it this way. 2 sigma 2 plus 3 sigma 1, 1. When I take the product here, I get 0. And when I take the product here, sigma 1, 1 squared is 1, I get 27. Wow. And that's the answer. Just on time. But we can think about this, and I will maybe give you a sort of wrap up next time. But this is the basic paradigm for how we use Chern classes. When we basically take the vector bundles we're interested in, try to express them in terms of simpler bundles, and use these 3 basic properties then to derive the Chern classes. You know what? It's now 11 o'clock and I should stop, so I'll do that. Talk some more about this next time.